Today we will be talking about how to attack game bots of AI-powered games. This is a joint work with our advisor and colleague. As we know, deep learning has become the hottest ML techniques. In the past few years, it has dominated many supervised and unsupervised learning fields. In security, it also outperformed the traditional methods in malware detection and intrusion detection. Going beyond supervised and unsupervised learning, reinforcement learning is a more powerful tool of learning technique that could handle more complex tasks. Recently, researchers combined RL with DL and developed different types of DRL techniques. These techniques has shown extraordinary performance in many decision-making tasks, such as robotic control, autonomous vehicle, finance, and business management. In games, agents learned by DRL also beat professional or even first-class human players. For example, DeepMind AlphaGo continuously beat first-class human Go players. More recently, news shows that besides Go game, DRL agent also could beat professional poker game players in different types of poker game, such as Texas Hold'em. Last year, DeepMind released an open source package which includes multiple board game environment and a state-of-art DRL learning technique, so users could train their own agent to play with other RL agents or even human player. In addition to board game, DRL also have become the standard method of training a master agent in both simulation games and real-time strategy games. In simulation game, OpenAI released a package called Jim, which includes different types of simulation game environment, such as the ones shown on the right-hand side, the Atari game, Robot School game, and musical games. So the user could test their DRL technique on all of these environments. Recent news also reported the effectiveness of DRL in world-famous real-time strategy games, such as StarCraft 2 and OpenAI and Dota 2. Along with the rapid development of DRL technique, researchers also start to investigate the security property of DRL, especially adversarial attack. As you may be aware, there have been many works about the adversarial attack on deep learning. So this attack can be mainly categorized as training phase attack and testing phase attacks. Since DRL system also have a deep learning involved, so intuitively, every DRL algorithm should also be vulnerable to the adversarial attack. This intuition has been validated by some recent works. Specifically, this work has shown that the attacker could perturb an agent's observation, action, or reverse, and force the agent to fail the corresponding tasks. However, as we will discuss later, these attacks are not practical, meaning because they involve hijacking a game system, which is time-consuming and cannot always guarantee to be succeed. So in this talk, we will present how to enable a practical adversarial attack against a game bot or master agent in a two-party game environment. This is the agenda for today's talk. We will start with some background knowledge of DRL. Then we will introduce some AI-powered games and how to train a bot for these games. Then we will introduce existing attacks on DRL game bots and discuss their limitation. Based on the limitation of existing work, we will elaborate on our attack methodology. Finally, we will show the evaluation result and conclude our talk. At a high level, an IL problem is a decision-making problem. in which specifically it has an agent who observes and interacts with an environment through a series of actions. Each time this agent takes an action, it will receive a reward. Take this Atari game as an example. In this game, the agent is the blue bot. The environment is just the game itself. At each time step, the agent observes the environment and take action accordingly. At this time, the agent probably gonna go right and try to catch the ball. After taking this action, the agent will receive a reward from the environment. So in this game, the reward probably be how many bricks the agent has hit. Then the game environment will receive this action and transit to the next state based on the transition dynamics. This transition dynamic is usually unknown to the learning algorithm. Solving an IL problem is equivalent to training an IL agent. The goal of this agent is to maximize its total amount of reward. So in this case, the goal of an IL algorithm is to learn an optimal policy, follow which the agent could receive a maximum amount of rewards over time. So as we can see here, the total amount of reward is very important for training an IL agent. In IL, it is represented by value function. Specifically, it has two forms. And an optimal policy can be obtained by maximizing either of the value functions. Take the game on the left-hand side as an example. Here, the agent could move within the checkboard and collect reward based on its move. Suppose we somehow know the value function shown in the figure in the middle. So based on this value function of each state, the agent will then choose its action. For example, on the top left corner, the best move here is to go right, because it will collect more reward than going down. In DRL, an agent is usually modeled as a deep neural network, which is called policy network. This network takes as input the observation and then output the corresponding action. Take the figure on the top right-hand side as an example. Here, the agent is the policy network shown here. This network then takes as input the game snapshot, that is the observation, and then output the corresponding action, such as going up, down, and either up, down, or left and right. So in this case, learning a policy is equivalent to solving the parameter of this neural network. The method that's used to solve the network parameters are called policy grading method. Recall, the goal of an DRL algorithm is to maximize the value function, but usually the value function of some complex game are usually unknown. So here in DRL, the policy grading method usually use another network to approximate the value function. As such, in each iteration of their algorithm, they will first update the value function network by minimizing the approximation error. Then they will update the policy network by maximizing the value function. As shown in the example on the bottom right-hand side, these two networks, they usually share parameter. Next, we will introduce some DRL power games considered in our work, and the code structure of training an DRL bot for these games. In this work, we focus on both the simulation game and the real-time strategy games. For simulation games, we are considering two-party mutual games. In this game, the observation is usually the current status of the environment, including the agent and its opponent's statics. The action of an agent is just the agent's movement, including like moving direction and moving speed. The reward of a game is the agent's statics and the win-lose condition. Going beyond simulation games, we also consider a real-time strategy game, StarCraft 2. In this game, the observation is the spatial condition of the map, and the amount of resources has been collected by the agent. The actions are categorized into 4 classes: building construction, producing units such as workforce and armies, harvesting resources, and finally attacking enemy. The reward of this game includes the game statistics and the win-lose condition. Recall that a policy grading framework is the standard way of training a DRL agent. Following this framework, researchers have developed different types of learning algorithms. Among this algorithm, the widely used one in training a game bot is the PPO algorithm. Here is the algorithmic workflow of a PPO algorithm. First, one needs to initialize the network parameter for policy network and value function networks. Then in each iteration, it first collects a set of trajectory by playing the current policy in the environment. So after collecting this trajectory, as is mentioned above, it will update the policy network and the value function network by using these trajectories. At the code level, take StarCraft 2 game as an example. To train a game bot, the first we need a programmatic game environment. With the environment by hand, the code structure is shown in the figure on the right-hand side. So basically, we need 3 major parts. First is the agent, which define and constructing the 2 networks, the policy network and the value function network for the agent. Then we need to write the environment wrapper by using the environment package listed above. So this environment wrapper are used to play the agent in the environment and collect the trajectory. Finally, the main file used to run the agent in the environment and train the networks defined above. To train a DRL game bot for 2 agent or multi-agent game, one standard strategy is the self-play mechanism. That is, training an agent to play against itself until the winning rate for both parties are 50%. Specifically, the main file for training a bot with this strategy is as follows. We first need to define a game environment by using the environment wrapper. So, as you can see from the upper right frame in the right-hand side figure. Then we define a runner to run the agent in the environment and collect the trajectory. Finally, we define a learner which receives the trajectory collected by the runner and update the policy network and the value function network. In the self-play mechanism, it will iteratively update the policy for each party until the winning rate for both parties stabilized at 50%. After introducing the basics of DRL and how to train a game bot or master agent by using a DRL algorithm, we now proceed to how to attack these game bots. Next, Xian will introduce the existing attacks on DRL game bot.
The existing attacks on deep reinforcement learning can be summarized as 2 categories. And the first one is the perturbation-based attacks. The second one is a more practical adversarial agent attack. Firstly, I will introduce the perturbation-based attacks. As we can see from the right picture, the adversary can either protect the observation and thus force the policy network to output a series of suboptimal actions, or directly add perturbations to the output actions of the policy network. Here is a pawn game example. We can see from the bottom image, two agents is playing the pawn with each other. For the current snapshot, the optimal action for the right agent is done before the attack. Then attacker generates perturbations by using the existing attacks on deep neural networks and adds it to the current observation to induce the right agent to output a suboptimal action. By doing so, the right agent may fail in this game. Although the perturbation-based attacks have achieved some success, it has large limitations in the real-world setting. In the game setup, it requires the attacker to hijack the game server. To illustrate this argument, we again take for example the aforementioned online games. In these examples, the activities of manipulating the environment means that adversary breaks into the game server or to the game coder and thus influence the environment that the agent interacts with. Considering this, it requires professional hackers tremendous effort and time. What's more, the perturbation-based attacks is not a practical setup for beating a master agent of a two-party game. Next, I will talk about the adversarial agent attack. As is shown in the right picture, the attacker is not allowed to hijack the information flow of the victim agent, but the attacker could train an adversarial agent by playing with the victim agent. Compared with the perturbation-based attack, it's more practical in games, since we need not hack the game system, and any player could play with the master agent freely. There is some existing technique in adversarial agent attack. In this work, it treats the victim agent as part of the environment and trains the agent to collect maximum rewards in the environment. Specifically, it uses the PPO algorithm to maximize the training agent's value function and expect to obtain a policy that could beat the victim. However, as we will show later, it cannot establish a high game winning rate. The reason is that it doesn't explicitly disturb the victim agent, and the training algorithm has less guidance for identifying the weakness of the victim. Next, Wenbo will talk about.
As is introduced by Xian, existing attack either rely on unrealistic assumptions or is not able to achieve a decent attack success rate. In the following, we will elaborate on our idea of training an adversarial agent to exploit the weakness of its opponent and thus defeat it in a two-party game. Our attack threat model is the same with the adversarial attack introduced before. But to tackle the limitation of this existing attack, we propose to augment it with two new designs. The goal of this design are the same. That is, train an agent to not only maximize its reward, but also prevent its opponent from collecting more reward at the same time. So in other words, we would like the adversarial agent learns to how to perturb or disturb its opponent. So specifically, our first idea is to directly change the adversarial learning objective to not only maximize its own reward, but also minimize its opponent's reward at the same time. Our second idea is to let the adversarial agent take an action that deviates the victim's next action. To realize the first design, Recall that the value functions are unknown to the learning algorithm. So the first step is to approximate the victim value function with another neural network. With this approximation by hand, we then add a term to the adversarial learning objective. This term is used to minimize this approximated value function. To give you an example of the difference between our objective and the existing attack, which only maximizes the adversarial agent's total expected reward. We use the collecting resources game as an example. In this game, the goal of an agent is to collect more resources than its opponent. Without the newly added term, the adversarial agent focuses only on itself. In other words, it will only optimize its policy and try to collect more rewards or more resources. However, if the victim agent or opponent agent has a better strategy of collecting resources, it will be extremely hard for the adversarial agent learns a better strategy than the victim and thus beat the victim. However, with the added term, in this case, the adversarial agent will learn to block the victim from collecting more rewards. So it will have a higher chance to beat its opponent, no matter how good the opponent's policy is. As for the second design, we first leverage a model explanation method to explain the action of the victim and find out the time step when victim takes action based on the adversarial agent. Then, in these critical time steps, we will optimize the adversarial policy to take an action that will introduce a maximum deviation in the victim's next action. Let me demonstrate this design with the example here. This is a robot school pong game in which the master agent, the purple one, is playing against the adversarial agent, which is the blue one. Recall, the observation of an agent is the current game statics, which includes its opponent. Here, the red frame in this vector indicates the adversarial part in the victim observation. So this observation is then given to the victim policy network and outputs the corresponding action. With the model explanation method, we could calculate the importance or inference of each input dimension on the output prediction. So as such, we could use this technique to identify the inference of the adversarial on the victim action. Just the red part in the victim observation. So the inference of the red part on output action. And select the time step when adversarial have a large impact on the victim. At these selected time steps, if we slightly change the action of the adversarial agent, it will also change the observation of the victim agent. So this small change in the victim's observation will then trigger a relatively large change in the victim's action. So this process is similar to adding adversarial perturbation to a deep neural network's input. So here, instead of directly change the vector value, we consider a more practical setup, that is, indirectly change the observation of victim by changing the action of the adversary. In this example, the trajectory in the gray canvas represents the ordinary trajectory. So here, the master agent could goes towards the ball and try to catch it and win the game. However, if we perturb the adversary's action, that is, choose a different action, in the critical time step selected above, at those time steps, the victim will then take a different action due to the perturbation. Like the trajectory in white canvas, here, the purple agent, the master agent, no longer move towards the ball due to the perturbation. As such, it cannot catch the ball and will lose the game. After introducing our attack methodology, we now evaluate it on some static games and show our interesting findings. Specifically, we choose 5 games, 4 of which are from musical game, and 1 is real-world strategic StarCraft 2 game. As for the musical games, the demonstration of the static game are shown on the right-hand side. The first game, Kick and Defend, is just a standard penalty shootout. In second You Shall Not Pass game, the runner, the blue agent, is running towards the red line, the finish line, behind the red agent. Then the blocker, the red agent, intends to block the blue agent from crossing the line. In both Human Arms and the Human games, the 2 agents are fighting against each other on an arena and try to push its opponent off the arena. As for the StarCraft 2 game, we consider a 2-party scenario where Zach versus Zach. Recall, an DRL algorithm iteratively updates the policy. We then measure and report the winning rate of the adversarial agent each time its policy is updated during the training process. Here is the comparison of the winning rates of the adversarial agent obtained by different attacks. The red line refers to our attack, and the blue line refers to the existing attack. As we can observe from these figures, our attack outperforms the existing attack on most games. The only exception is the Human Arms game. In this game, both attacks cannot improve the attack success rate of the adversarial agent. The reason is that the observation in this game is of a low dimensionality, which means the perturbation space is relatively small. As such, it's kind of hard to disturb the victim where the adversarial action and defeat the victim accordingly. However, as is shown in the figure below, our attack improves the non-lose rate of the adversarial agent. As we will explain later, dispel cannot influence the action of the victim agent. Our attack could give the adversarial agent some advantages by exploiting the vulnerability of the game design. After showing the quantitative evaluation, we now show some game episodes of our adversarial agent play against the victim. First, as we can see from the Kick and Defend and the You Shall Not Pass game, our attack could exploit the weakness of the victim agent by establishing some weird behaviors. In human video, So in human video, our attack could help learn a better strategy, that is, initialize itself near the boundary and lure the victim to attacking it and fail from the arena. More interestingly, in the summon ounce game, we can see that adversary intentionally fall from the arena. The adversary intentionally fall from the arena after the game beginning. In this case, the game ends up with a draw. This shows that our attack could explore the weakness of the game rule, because one of the rules is that if one player or one party fall from the arena without touching its opponent, the game ends up with a draw. So here, the adversarial agent use this rule to force the game ends up with a draw. In addition to the attack, we also consider a possible defense that is widely used, the adversary retraining strategy. Specifically, we play the victim agent with our trained adversarial agent and retrain the victim agent with our proposed attack. The results are shown in the figure in this slide. As we can observe from the figure, the adversarial retraining process indeed improves the performance of the victim by winning the you should not pass game and achieving a draw on the other 3 games. But however, it doesn't work on kick and defend game. We suspect this is caused by the unfairness of the game design, because we have tried that it's relatively hard for the kicker to win the game in general. Here are some videos of using the retrained victim agent play against the adversary. In the first video, the you should not pass game, the victim learns to ignore the adversary and directly go for the finish line, which means the victim agent will be aware of its policy weakness and patch the weakness through the retraining process. In the second video, the victim recognizes the trick played by the adversary. It will stay where it is, so the game will end up with a draw. Which means in this human game, the victim also realizes its policy weakness and try to fix it. In the summon ounce game, since the victim cannot change the intentional behavior of the adversary, so the retraining process basically still keeps the original behavior of either victim, both victim and adversarial. So the game still staying as tie games. Finally, in the kick and defend games, as we mentioned above, the victim acts even worse. It's more easier to fall into the ground, trigger it to lose the game. Finally, we conclude this talk with 3 conclusions. First, attacker could train an adversarial agent to defeat and game bot for an AI-powered game. We also found that by disturbing the victim action, the adversarial agent could exploit the vulnerability of both the victim agent and the game rule, and thus fail the victim agent more effectively. Finally, we show that adversarial retraining does not always succeed. We may need more advanced techniques to protect the game boss and master agent. Thank you very much for your attention. We now open up to answer some questions.
Okay, hello everyone. I'm Wenbo. Thanks everyone for attending our session. Since at the beginning of this session, the self-introduction was missing, so I'll just do a reintroduction here. So I'm Wenbo, I'm a PhD student at Penn State. So this work is a joint work with my advisor Xinyu and my colleague Xian and Jimmy Zhu. So the main speaker of this talk was me, and Xian took a small part of it. So the speakers are Wenbo and Xian. So before I answer any questions, so there are some questions in the question chat box. I just want to clarify some things. Okay, first, this work is about attacking a master agent in a deep reinforcement learning environment. Is I say we have like so many online games. Some of you may aware some like news talking about AI game bot beating professional player in Dota 2, StarCraft 2, those type of games. And with the success of AI and like deep reinforcement based game bots, more and more games are using this type of bots instead of like rule-based bots as their master agent. So maybe there is some agent trained by deep reinforcement. The goal of our attack is to attack such type of agent. And so currently, we have some like we will like about the code of this attack. We will open source it, but currently we are still under construction. It will be open source like in like 1 month, I think. We will do like as soon as possible. Okay, so I received some question in the chat box. The first question, I think they're all like very good questions. The first is about whether this attack. So Hunter asked about this, whether it's an attack just for multi-party game or like not cooperative games. So that's correct. Our attack is only works in the multi-party competitive game scenario. So to be more specific, currently we only do two-party game. So we would like to extend the game to multi-party game in the future. And he also asked about the idea of this attack is to affect the learning of the victim. So actually, as I just mentioned earlier, since we are attacking master agent, so here our victim agent in our scenario, its policy is pre-trained, which means that during the attack process, the policy of the victim agent is not learned. So our attack is just to learn our own agent and try to perturb or like influence the action of the victim agent, force it to make some wrong choices, and thus lose the game. So we are not affecting the learning process of the victim. We are affecting the actions of the victim agent during the game. So another question is about, are you trying to train both model adversarially? So that's also a good question. So as I mentioned earlier, during the attacking process, we only train one model. That's the adversarial model. So we have two parties, the victim party and the adversarial party. The victim party is pre-trained. So during the attack process, we only train our adversarial model to try to beat the victim model. But we also try to defend this attack. So during the defense process, we do the things in turn. Is that we fix the adversarial model and try to retrain the victim model. See if the victim model can learn to beat the adversarial model again. So just like at one time, we only train one model. So another good question is about how to transfer the attack to interface of such API in the real world. That's also a good question. So currently we are doing StarCraft 2, which means like if there is an API, real world API about StarCraft 2 like online game, so we could do that. We can directly apply our attack to defeat the master agent in the StarCraft game, because StarCraft 2 is a real world game. And there are also some like other online APIs for other games, such as Go game, poker game, different type of poker games. So the ongoing work focuses on how to extend our current attack on the StarCraft 2 games to those type of games. So if we could like build a bridge between StarCraft 2 and Go and poker and some other games, so our attack could be potentially generalized to those type of APIs. Actually, that's all the questions I received in the chat box. Yes, thanks everyone for your time. And if you have any other questions that you want to like talk more about this work, you can contact me with any ways you prefer. Thanks everyone for your time.